Okay, listen closely, because we are about to completely change how you approach your exams. Welcome to this Masterclass Explainer. I'm your host, and today we are stepping out of the role of the standard student and adopting the mindset of a hacker. Now, we aren't hacking computer networks here. We are finding the backdoor into the Cambridge Computer Science exam system. We are going to decode the mark scheme. Whether you're sitting syllabus 417, 478, 2210, or even 9618, the strategy we're going to unpack today is your master key. Work smarter, not harder, right? Let me paint a picture for you. Imagine you're sitting in the exam hall. The clock is ticking down, the pressure is on. On the left side of the room, we have a student named Alex. Alex is an absolute machine when it comes to revision. Alex has memorized every single computer science fact, every definition, every truth table, every data structure. Faced with a 6-mark question on binary addition, Alex panics and unloads a mountain of raw, disconnected facts onto the paper. Alex is just word-vomiting theory, completely ignoring the specific real-world scenario the examiner actually asked about. No analysis, just facts. Then, on the right side of the room, we have Sam. Sam is rushing against the clock, constantly looking at the timer. Sam reads the question, completely misses the crucial command words, like explain or evaluate, and writes a vague, single-sentence answer that barely scratches the surface. So what do Alex and Sam have in common? Well, when the examiner's red pen hits their papers, they both lose massive amounts of marks. They both leave that exam hall feeling super confident, thinking they crushed it, and they both end up with a fraction of the grade they actually deserve. We are going to fix that exact problem today by looking specifically at the foundations of binary addition and overflow and showing you how to extract every single available mark. So we have to start by asking this absolutely central question. Why do smart, incredibly hardworking students lose marks on topics they have literally already memorized? I mean, think about it. If you know the exact textbook definition of an overflow error, why are you getting a 2 out of 6 on the exam paper? The answer is that relying purely on a vocabulary list without understanding the practical context is a massive, dangerous trap. It is what Cambridge examiners constantly refer to in their reports as the safe but shallow trap. You're sitting there, you read the paper, you recognize a familiar word like binary or overflow or register, and your brain instantly goes on autopilot. You start answering the question you wish was on the paper, or you just write down the definition you crammed into your head last night, instead of answering the specific scenario that was actually set in front of you. In computer sciences, especially at this level, a definition is literally just the starting line. As our source material clearly points out, so many avoidable losses of marks happen because candidates treat concepts as isolated terms rather than connected digital structures. We have to break the habit of just listing facts. The examiner already knows the facts. They want to know if you can apply them. To transform your answers from red pen disasters to green check marks, we're going to follow a highly specific blueprint today. First, cracking the exam code. Second, the 3-layer method. Third, structuring high-scoring answers. Fourth, real-world connections. And finally, the ultimate self-check. Let's get straight into it.
Part 1. Cracking the exam code. This is where we break down exactly what the examiner is secretly begging you to do.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's look at a vital discipline, separating description from explanation. This is where we decode those Cambridge command words. A description tells the examiner exactly what a device, process, or method is. It's safe, but it's shallow. It hits assessment objective 1, basic knowledge. But an explanation tells the examiner how it works and why it matters. That's hitting the higher assessment objectives. Examiners expect both. If you only describe, you might get 1 measly mark for identifying the concept. But, and this is a big but, if you jump straight into explaining without clearly naming the concept first, your response sounds totally confused. The examiner thinks, do they even know what they're talking about? This is where the Peel framework becomes your ultimate weapon. Point, evidence, explanation, link. Your point is your description. Your evidence, explanation, and link form the how and why. Let's do a quick mental challenge right now. I'm going to read 2 answers. I want you to spot which one follows the Peel framework and perfectly balances description and explanation. Answer A, this is our buddy Alex. Binary overflow is when a number is too big for the computer, so it drops a bit and causes an error. Answer B, binary overflow occurs when the result of an addition requires more bits than the allocated register can store. For example, adding 2 8-bit numbers that result in a 9-bit answer means the most significant bit is lost. This results in data corruption within the system. Obviously, answer B is the winner. It names the concept clearly as the point, provides evidence of the 8-bit to 9-bit jump, explains the exact mechanism of the lost most significant bit, and links it to the ultimate consequence, data corruption. That is a full-mark answer. So, the absolutely crucial takeaway here is that binary addition and overflow must be viewed as a connected computer science structure. It represents a real, tangible digital problem with severe practical consequences for everyday users and massive industrial systems. It is not just an isolated vocabulary term floating around in a textbook index. Think about it like this. Have you ever seen a classic video game glitch out? Think of the famous Pac-Man level 256 screen corruption, where half the screen turns into unplayable garbage. That wasn't magic, and it wasn't a virus. That was an integer overflow. The game's code literally tried to store a value larger than the 8-bit register could mathematically handle, and the whole system broke down. By framing binary arithmetic as a real digital mechanism that belongs to a much larger web of ideas, like data representation, memory allocation, and system architecture, you actually give your brain a reason to care about it. When you understand the physical consequence, the abstract concept sticks in your memory permanently. You stop memorizing, and you start understanding.
Moving on to Section 2, the 3-layer method. This is how we move from basic understanding to elite exam performance.
This method systematically moves you through 3 distinct layers of understanding. First comes the simple explanation. This is everyday language. If you can't explain it to your grandmother or a 5-year-old, you don't actually understand it yet. For binary overflow, your simple layer 1 explanation is, hey, you try to pour a gallon of water into a pint glass and it spilled all over the floor. Boom, concept grasped. Second comes the technical explanation. This is where you inject the correct Cambridge subject vocabulary. Now we say, an 8-bit register has a maximum decimal value of 255. If a binary addition operation results in the number 256, a 9th bit is generated, which cannot be stored in that specific hardware. Third comes the exam explanation. This is the hardest part, and it's where students like Sam fail. This is where the idea is shaped into a high-scoring response under brutal time pressure. Students constantly fall into the trap of thinking they are totally ready for the exam just because they've mastered layer 1 or layer 2. But the exam hall demands layer 3. Layer 3 means seamlessly integrating that technical vocabulary with the highly specific scenario provided in the prompt, clearly stating the step-by-step mechanism and defining the exact consequence for that specific user.
So how do we practically achieve that layer 3 mastery before exam day? By structuring your revision timeline into 3 distinct passes. Pass 1, secure your definitions and key contrasts. This is foundational. You need to instantly know the difference between memory and storage, between a compiler and an interpreter, between an 8-bit and a 16-bit register. Pass 2, rehearse worked explanations and logical sequences step by step. Don't just read them, write them out. Draw out the binary addition truth tables. Physically trace the carry bits with your pen so your brain maps the sequence. Pass 3, adapt the context. This right here is the true hacker move. Once you know the sequence, you mix up the terms. Change the scenario from a school database to a secure banking application or a factory robotic arm, and force yourself to rewrite the PL paragraph for that new scenario. This layered structure is incredibly powerful because in Cambridge computer science, knowledge is constantly reused and remixed across different chapters.
Section 3, structuring high-scoring answers. Stop scrolling. Subscribe to our YouTube channel, AC Exams, at ACExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at ACExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to building that perfect answer structure.
Here is the absolute disciplined path you must take when your pen hits the paper. Step 1. Identify the demand of the question. Decode the command word. Is the examiner asking you to describe, explain, evaluate, or compare? If it says evaluate and you just describe, you are throwing away 50% of the marks instantly. Step 2. Classify the concept. Read the scenario and lock onto the fact that, underneath the confusing story about a factory, this is just a data representation issue, specifically an overflow error. Step 3. Explain the sequence step by step. Do not jump around. Start with the binary addition process, show exactly where the extra carry bit is generated, and state the physical reason why the register rejects it. Step 4. Connect back to the context. This step is the magic bullet that prevents you from writing random facts like Alex. If the question asks about an industrial temperature sensor, your final link in your PL paragraph must explain how the overflow causes the temperature sensor to report wildly inaccurate data, potentially causing a machine overheating issue. This logically ordered, context-driven sequence is exactly what turns a C-grade answer into an A-star answer. I need you to mentally highlight, underline, and burn this warning into your mind. It appears in almost every single Cambridge Examiner report. Generic responses rarely gain full marks. If the exam question is set in a school library, an office, a retail checkout, or a secure network, your answer must actively stay inside that context. If you give a brilliant textbook-perfect explanation of binary overflow, but you don't mention how it affects the school library's book checkout system, the examiner is forced to cap your marks. You have to prove you can apply the theory to reality.
Which leads us perfectly into Section 4, Context and Real-World Connections. This is where we convert raw, memorized data into actual exam usefulness.
The core mathematical patterns behind binary addition and overflow appear quite literally everywhere. They are functioning right now in your phones, in global banking systems, in automated robotics, in school management tools, and in secure websites. While the surface features of the exam question might change from year to year, the core binary process you need to explain remains mathematically identical. Let's do our first interactive workshop challenge right now, the data scan. I want you to imagine a complex chart in front of you. It's showing an automated robotic arm in a massive car factory. The arm's movement is controlled by a basic 8-bit microcontroller. The chart shows the arm's position coordinates increasing sequentially: 250, 251, 252, 253, 254, 255, and then suddenly, instantly, the next reading drops to 0. The robotic arm swings wildly back to its absolute starting position, smashing completely through a car windshield on the assembly line. I'll give you a few seconds to extract the core trend here. What exactly happened at coordinate 255? Okay, if you applied the hacker mindset, you didn't panic at the confusing mention of a robotic arm or a car factory. You scanned right through the surface distraction and identified the core computer science trend, an 8-bit integer overflow. You know that 255 plus 1 in 8-bit binary results in 256, which mathematically requires 9 bits to store, a 1 followed by 8 zeros. The hardware system physically dropped the most significant bit, that 9th bit, reading only the remaining 8 zeros, so it read the number 0, causing the catastrophic physical reset. This is how you apply binary theory to a mechanical system to secure top marks.
This quote from the source material hits the absolute nail on the head. Real-world transfer matters because it converts memory into usefulness. Leaving your ideas floating in abstraction is how you bleed marks. Let's do challenge number 2, find the flaw. I'm going to read a sample paragraph from a student answering a past paper question about a banking system error. Your job is to listen closely and identify the exact sentence that is losing the marks. Here's the student's answer. The banking system crashed because of a binary overflow. Binary overflow happens when a calculation produces a number that is greater than the maximum value the allocated storage can physically hold. For example, adding 1 to 8 ones results in a 9-bit number. The extra bit is dropped. This is bad for the bank. Did you spot the flaw? It's right at the end. This is bad for the bank is a painfully generic response. It lacks any real-world transfer. A high-scoring, PL-structured answer would take that final link and say, this results in the most significant extra bit being dropped, meaning a customer's massive financial deposit could be registered as a near-zero balance, causing severe data corruption in the banking ledger. Context is absolutely everything.
Section 5. Traps and the ultimate self-check. Let's look at how to bulletproof your answers.
Examiners constantly note these specific, recurring errors that distract from the core mechanism and cause highly avoidable mark losses. First, vague wording, saying it breaks instead of data is corrupted. Second, confusion between similar terms, like a student confusing a compiler with an interpreter or interchanging memory with storage when they mean very different things. Third, missing steps in a process. This is huge. This is where a student skips straight from binary addition to system crash without actually taking the time to explain the dropped carry bit in the middle. And finally, stating an advantage or consequence with absolutely no reason attached to it. Let's do our final interactive challenge, speed writing. You have a few seconds to mentally draft a perfect PL paragraph avoiding all these traps. The prompt is, explain how binary overflow affects an online retail checkout cart restricted to an 8-bit item counter. Think about your point. Think about your evidence and explanation of that specific 8-bit limit. Think about the link to the retail cart consequence. Your ideal top-tier answer should look exactly like this. Binary overflow occurs when an addition result exceeds the allocated storage space. In an 8-bit counter, the maximum decimal value is 255. If a user adds a 256th item to their cart, the calculation requires a 9th bit, which the register cannot physically store. Consequently, the most significant bit is discarded, resetting the user's cart counter entirely to 0 and causing the frustrating loss of all their selected items. That is a flawless, context-driven answer.
You see, clarity of sequence is vital in process-based computer science topics. Look at the difference between a flawed sequence and a winning sequence. A flawed sequence jumps forwards and backwards constantly. It mixes general theory with the context in a way that completely breaks the logical flow. It starts with the website crashing, then abruptly mentions binary math, then jumps back to the user being angry, then mentions the 8-bit limit. It's a mess to read. A winning sequence, on the other hand, is perfectly chronological. You explain the underlying mechanism first, the mathematical addition of the binary numbers. Then you explain the physical capacity limit, the hardware of the 8-bit register. Then you explain the physical result, the dropped 9th most significant bit. And only finally, at the very end, do you state the consequence, the corrupted user data or the system failure. Never do those steps in the opposite order.
To ensure you never fall into the flawed sequence trap, we use the ultimate self-check. This is a brilliant, practical 4-question system you can use during your pass-through revision. Whenever you finish studying a concept, ask yourself, 1. What exactly is it? 2. How does it work step by step? 3. Where is it used in the real world? 4. Why is it better, worse, or problematic in that specific situation? If you can answer those 4 prompts out loud, without peeking at your notes, that topic is fully ready for the exam hall. If you stumble on question 3 or 4, you are not ready. You need another cycle of reading, explanation, and recall. This 4-question check completely encompasses the rules that guarantee top marks.
I'll leave you with this final, provocative thought. Test your newfound hacker mindset right this second. Look away from the screen. Can you answer those 4 questions for binary overflow out loud? What is it? How does it work? Where is it used? What is the consequence? If you can, you've just successfully found the backdoor into the mark scheme. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep hacking those past papers, keep applying the structure, and I'll see you in the next session.